Hello everyone. This lesson is more of a supplementary lesson for all of chapter 3, and this is going to be focusing on set theory and the language of probability. So we talked about some of this before, but I'm going to start from the beginning and also cover some things we may not have covered in class so far. So the first thing is we talked about the complement. So the complement could just be thought of, and I'm going to do this in terms of A and B, but in this case, for A, the complement would be not A, which means basically whatever A is, the complement is everything else. So for example, if I am rolling a 20-sided die and A are even numbers, then not A would be not even numbers or the odd numbers. And the way that we write things like this would be, we'll usually use something like A with a little c, or A with a tick mark, or A with a dash. Again, you might see things like tilde A, or you might see this little symbol and A. These are all ways of writing the complement. The way that we visualize these logic statements in set theory is we draw what's called a Venn diagram. So this is a Venn diagram. And what we do within this box represents our sample space. It's everything. So whatever's within this box is our sample space, which is all of the possible outcomes. So if I have some set in here, this is A, then everything that falls outside of that will be not A. So if I were asking for what is in not A, it would be everything in the sample space that is not within A. Now, if I were asking you for what is A would just be then I highlight what's within A and I leave everything else around it blank. The next thing I wanted to kind of talk about are unions. Unions, which have the symbol like this. It's like a U, but with no tail. This is often referred to as an or statement. And this is actually where the language comes in, because when you're reading a problem and we say, what is the probability of this or that? That's the indication that this is a union. So for example, if you had the probability of A or B. Now, or a union, what it means is it will take anything that's in A, it will take anything that's in B, or anything that is in both. So to draw this out, what this would look like is something like this. I have A right here. I have B right here. And it will take anything from A, anything from B, and of course, anything from either of them at the same time, because it also counts the intersection. So the only time a union is false is when something is not in either of them, right? So what this means is that, for example, if I had that A is equal to 1, 2, 3, and B is equal to 2, 3, 5, 6, it would be A union B equals, and then it's everything that is in A or is in B. So in this case, 1 is in A and B. Or sorry, 1 is just in A. 2 is in A and B. 3 is in A and B. 5 is in B. 6 is in B. And remember, whenever we're writing sets, we only put each outcome one time. So A or B would be 1, 2, 3, 5, 6. So this is a union, also known as an or statement. An intersection which has the symbol like the union but flipped upside down, this is known as an and statement. So for example, if you're ever looking at a problem and ask you what is the probability of this and that occurring, this would be an intersection. So going back to our card problems, or a union would be something like, what is the probability that I get a black card or a jack card, meaning that any black card will work. Any jack will work, including the black jacks. For an intersection, it would be, what is the probability the card I get is black and a jack? So what this means is it has to be both conditions to be true at the same time, meaning that a red jack will not work. A black card that is not a jack will also not work. The only thing that gets filled in for an intersection will be whatever they have in common. So going back to our prior example of A being 1, 2, 3 and B being 2, 3, 5, 6, then A and B would be equal to the only thing that they have in common. So curly bracket 2, comma 3, because 2 is in both of them and 3 is in both of them. So these are the foundational statements that we will be using in logic, which of course we use quite a bit in probability. You've got complements, which is not. You've got unions or statements. You've got intersections or and statements. And you'll actually hear me throughout the course. I will focus a lot on this because this is true in almost all of math. So for example, if we ask you, what is the probability of getting this or that, you know it's a union. But it might also be something like, these assumptions are true for this to happen. This or this, meaning that as long as one of them is true, I can use this method. Whereas an intersection would be, this and this must be true, meaning that it only works if both are true, not if one is true or the other, only if both are true. Okay, so now we're going to talk about a few slightly more advanced topics. The first one is events that are independent. So events that are independent means that they are not impacted by any other event. So examples of this would be something like coin flips. If I flip a coin and I get heads, and I go to flip a second coin, that first coin flip has no impact on my second coin flip, just like it has no impact on the third coin flip or the fourth coin flip. They are independent from each other. So this means that if I were to do these probabilities, this will actually impact how we find them. And I'll show you in a second what I mean by this. Another important definition we have are events that are mutually exclusive. So mutually exclusive events are events that if one happens, it means the other could not have happened. An example of this would be, if I draw a card and I tell you it's red, then mutually exclusive from that, it could not also have been black. So you can't say, okay, what's the probability that I get a red card that's also a black card? And we'll talk more about this whenever we get into the multiplication rule of probability. But mutually exclusive just means that two events cannot occur simultaneously. If one occurs, the other one could not have occurred. Okay, so an example of this would be that if I, grab a card and I tell you that the card is a face card, then you know for a fact that it could not be a number card. You know that it cannot be an ace because I told you specifically that it's a face card. So you can't say, what is the probability that I get a face card and also a number card, unless I'm drawing more than one card, in which case that'd be a different kind of problem. So now how does this actually work though? Well, it actually works because if I show you the formula to find the probability of a union, probability of A or B, this is going to be the probability of A plus the probability of B minus the probability of A and B. And we'll talk more in depth about this when we're at that section, but the reason we have to do this probability of A and B is if you look at the image that we drew in our Venn diagram, whenever we looked at A or B, what happened? Well, we counted everything in A. We counted everything in B. This area in the middle, we double counted. So basically what we're doing is we're saying the probability of everything in A plus the probability of everything in B. But we've double counted the probability of A and B, so we have to subtract one of those out. So in this case, if I have an event that is mutually exclusive, this means that if I were to draw this Venn diagram, A and B, they have no overlap with each other. So if I am looking at an OR statement and the events are mutually exclusive, this means that it would just be probability of A or B equals the probability of A plus the probability of B. Now, I mentioned previously when we were looking at 3 of our definitions of probability about that one where it was we have some events E1, E2, E3 up to En that are mutually exclusive. And if we take the probability of E1 or E2 or E3, it ends up being the probability of E1 plus probability of E2 plus probability of, up to probability of En equals probability of the sample space, which is equal to 1. That's actually the principle that we're using in this case because it specifies that they are mutually exclusive, meaning that they have no overlap. Revisiting that definition we had earlier, we had some events E1, E2 through En, which were mutually exclusive. So we talked about the fact that mutually exclusive means 2 events cannot occur simultaneously. So to write that in terms of set theory, that would mean that if we had some events A and B, A and B equals the empty set. Because as we showed in our Venn diagram, they have no overlap. So therefore, A and B is nothing. Nothing is in both A and B. So if we were to take the probability of A and B, this would be equal to 0. Going back to our definition of E1 through E2, E1, E2 through En, where we had that they were mutually exclusive, this stated that if I take the probability of E1 union E2 and find the union of all of these, that this is going to be equal to the probability of E1 plus the probability of E2 up to plus the probability of E sub n. And then all of these together make up the sample space. And we know from our first definition of probability that this is going to be equal to 1. And really what this is kind of describing is actually what's called a partition. A partition is just that if I have some sample space and every possible outcome is accounted for, but there's no overlap in them. So this would be something like E1, E2, E3, E4, and E5. And this is called a partition. It is just that if I take the probability of every single one of these, because they account for all the possibilities, there's no overlap between them, that they will be the entire sample space. So therefore, the probability of all of them is equal to 1 when you take them as a union. So you might wonder, again, why this is important. Well, anyone who's worked, again, in computing, this is actually a concept used in computing. Whenever you have a hard drive, most hard drives have partitions to them, meaning certain places the data is located based on something. So like E5 might be your operating system. E1 might be devoted to something else. But you cannot write between them because they are separate. They are mutually exclusive from each other. You are either in this partition or you are in this partition. You are not split between the two. They have no overlap with each other. You can't have data that's in both E1 and E5, unless, of course, it's a copy, but you can't have the same data between them. And as I mentioned before, a lot of these concepts, all of these concepts, are actually used in computing. So we have these things called logic gates. Well, you've learned about complements, well, or not. All those terms, those English versions of the words, those are actually what are used in computer science. For example, you have something called a NOT gate. And a NOT gate literally just takes an input. So if I have a 0 come in, it changes it to not 0, and a 1 is output. If a 1 is input into it, it takes that 1 and gives you a not 1 or a 0. So this is called a NOT gate. A union has the OR gate, which is to say that if I have a 0 and a 1, it will give me out a 1 because one of them is 1. If I have instead this is 0 and this was 1, I will still get a 1 out. If I have a 1 and a 1 will come out. And the only time that a 0 will come out is if both of them are not true. So this is called an OR gate, where everything it looks at, is there a 1 on input A or input B? If one of them has a 1, we're good to go. If the other one has a 1, you're good to go. If both of them have a 1, you're good to go. The only time that it sends a 0 out, or a negative signal, would be if both of them had an input of a negative signal, or a 0. An AND gate is where it has to be both have inputs of 1. So this would be something like if I have 1 and 1 and I input into the gate, I don't remember the exact symbols they use, but something like this, then you'll be output of 1. If I have one of them is equal to 0, then, but both must be true, right? You can think of it in terms of true and false. 1 is true, 0 is false. If I have 0, 0, I get a 0. If I have 0, 1, I still get a 0. It is only sending out a positive signal when both A and B are in the on position. And this is literally the foundation of every electronic device you've ever used in your entire life, from your cell phone to camera to computer, any technology, radio, it uses these logic gates. And they can actually be combined. So for example, if I have an OR gate, I can actually also have a NOR gate, which is not OR gate. So it takes the same idea of an OR gate, but anything that would come out as a 1, it changes to a 0. Anything that comes out as a 0, it changes to a 1. You could also have, instead of an AND gate, you could have a NAND gate, where anything that comes out as a 1, it changes to a 0. Anything comes out as 0, it changes to a 1. You can also have things like, instead of an OR gate, you could have exclusive OR. And this is where it's going to come into play with mutual exclusivity and stuff like that. But I just wanted to give you a brief introduction to some of the terms and language that we're going to be using. And it is very relevant. We're going to be using it all throughout Chapter 3, and we will also use a lot of this language throughout the rest of the course. But you'll also see it in a lot of other courses. If you take other math classes, you will see in certain places where they use the term AND, or they use the term OR, and generally mathematicians and statisticians are very precise with those words, and we do actually mean, if we say OR, it means this or this. If we say AND, we mean this and this must be true, things like that. So I just want to give a brief introduction and also kind of show you where all this might come into play, and also retouch on that definition that we had to kind of gloss over in the beginning of the section. So that's it for my quick introduction to set theory, and hopefully this will help you with your probability. Understanding the language will go a long way in doing well in this section. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.